Good day. This is going to be the third part of the Chapter 11 pre-recorded notes. Hopefully we're going to be able to finish them off in this last section. Now, last time, there's a couple samples involving phase change that I didn't actually complete yet. So first thing we're going to do is look at some phase change sample math, and then we're going to look at the math and concept of the rate of thermal conductivity. So a lot in this one part. Let's go ahead and get started. We ended last time having gone through sort of the process of what has to happen as an object, say, heats up, melts, heats up, evaporates, and then everything that would happen reverse as well. And now we're going to look at the math behind that and how to utilize the Q equals ml, heat equals mass times latent heat formula in conjunction with Q equals mc delta T as well, since Q equals mc delta T describes the warming and cooling process, and Q equals ml describes what's needed in order to actually induce a phase change. And the two need to work together, as we're going to show here. So, first sample we're going to look at. Let's say we have 0.1 kilograms of 115 degrees Celsius steam. So we're starting at very hot steam, and we want to turn it into 45 degrees Celsius water. So we're going from hot steam, cooling it down into water. We're going to look at the math behind all the different steps that are needed in order to do that. We're going to come back to the second math question here. This next slide shows my work for both parts. We're just going to focus on the first part for right now. So we need to figure out how much thermal energy needs to be removed from the steam in order to turn it into water. And what I'm going to do here is I'm showing all of the different stages added together. So, delta Q steam, I want to know how much thermal energy needs to be removed from the steam in order to accomplish our objective. First, the very first thing that has to happen, as you remove thermal energy from the steam, since it's not at its boiling temperature, it's warmer than boiling, since boiling point of water is 100 Celsius. Currently, according to the sample, we're starting at 115. If you cool this steam down, the first thing it's going to do is cool off. It's not going to start turning back into water yet. First thing it's going to do is reduce its own temperature to get to the temperature at which it will condense back into water. So the first step is going to be mc delta T as we cool the steam off from 115 down to its boiling point. Boiling point of water is 100 Celsius, so it's going to, this particular stage is going to end at 100 Celsius. It starts at 115 Celsius. So this step right here is how much thermal energy needs to be removed from the steam in order to turn it into 100 degrees Celsius steam before we can start doing the phase change. The next step is going to be, once you have it at 100 degrees Celsius, now as you remove thermal energy from it, now it will begin turning back into water. And so, the next step is going to be using Q equals ml to figure out how much thermal energy needs to be removed from that steam to complete this phase change. So we'd have the steam's mass here times the latent heat of vaporization for steam. Then, once this step is completed and we've removed all of the thermal energy needed to turn it back into water, now what we have is 100 degrees Celsius water. So the next step is going to be taking that water and cooling it down to our end temperature by removing more thermal energy. So since we're reducing temperature again, this is going to be another mc delta T step. So mass of the steam times specific heat of water times the change in temperature from 100 Celsius down to our end point of 45 degrees Celsius. So each of these three parts represents a different part of that chain. First is cooling the steam down, then is actually turning the steam into water, then is cooling the water down. And I recommend getting all these different parts planned in your head, organized on paper, and then we're going to need to make sure that we use the correct constants in each part of this lump sum here. Let's look at the first part, just the part where we're cooling down the steam. First thing we're going to need is the mass of the steam, which is going to be consistent throughout this entire question. We have, according to the problem text, 0.1 kilograms of steam. So that's going to be our mass for this entire first part. So mass of steam becomes 0.1, and that'll be used for the mass of the steam in every single part of this, because even as it's changing phase, it's still the same amount of material. Its mass doesn't change just because it's cooling down or undergoing a phase change. So steam mass is 0.1. Next, we need the specific heat of steam. And even though water, steam, and ice are all technically the same substance, they have different specific heats depending on which phase they're currently in. So we actually do need to scroll back a few slides to look up the specific heat for steam. So I've tabbed back to a previous example that has a specific heat table on it. And specific heat, steam is 2010 joules per kilometer degrees Celsius. While we're on this particular slide, I'm going to go ahead and point out specific heat for water again, 4,186. And additionally, because we'll need it later, the specific heat of ice, 2,090. So we have those specific heats to be able to use later. So specific heat for steam is going to be the 2010, like the table told us. And then the delta T, we're going from 115 down to 100, so that's going to be a change of negative 15 degrees. There's a small thing I want to point out as we're transitioning from this first piece of the formula into the second piece. And I admit this is a little less of a formula and more of just a sort of lump sum of all the different formulas representing the different phases. In this first piece here, and equally so in the last piece, since they're both based on MC delta T, since we're cooling the steam and then the water down, these parts will inherently have negatives in them. In this first part, we're decreasing temperature, so this first piece will inherently become a negative number just from what you plug into it. Same with the last piece. We're cooling down, going from 100 to 45. The middle piece, the ML part, does not have anything inherent to it that will set it as a negative number if you are cooling something off. If you were to add an ML term into something because you need to factor in the energy of a phase change, you yourself are going to have to take into account whether or not that phase change is adding thermal energy to the object or taking thermal energy away from the object. In this particular case, since in order to turn steam back into water, you have to remove thermal energy from it, I have manually set this term as a negative because you have to be subtracting thermal energy to turn turn the steam back into water. I had to manually add that negative sign there because the formula doesn't have a way to factor that in by itself. This is something you have to set manually. But, so for this next term, we've got the negative out front. That's important. We do need it. Next is the mass of the steam again. It's going to be the same mass term for this entire part of the question. And then we need the latent heat of vaporization for steam. Since we're undergoing a phase change involving gas to liquid or vice versa, that specifically requires latent heat of vaporization as opposed to latent heat of fusion. So let's tab back to previous slide that has the latent heat chart on it. We're going to look down to the entry for water and look at the latent heat of vaporization for water is 2.26 times 10 to the 6th. So that's the value we want right now since we're going from steam to water. It'd be the same value if you were going from water to steam. Any liquid to gas or gas to liquid change, you need the vaporization latent heat constant. So that's the value we will plug in for the latent heat of vaporization for steam, 2.26 times 10 to the 6th. And then the last term, this step represented turning the steam into water. So this last step is going to be cooling the water down. So it's the same mass of material because it's the same matter. It's just in a different state now, so it still has the same mass of 0.1, but now that it's water, we need to use water's specific heat of 4,186. Not the same one as steam. Now that it's water, we need to use water's specific heat. It's very important. And then the temperature change now, we're going from, as soon as the phase change is done, now you have 100 degrees Celsius water, and now we're cooling it down to 45 degrees Celsius. So that's going to be a net change of negative 55 degrees Celsius. That's everything, every variable we need to find our total heat change. As I said, every term needs to become negative. The MC delta T's will handle the negative sign themselves. You will have to make sure to check and add a negative sign manually if you are doing a phase change involving the removal of heat. We multiply each of our terms to simplify them. That gives us 3 big negative numbers. And so our final answer will be negative 252,038 joules of thermal energy that needs to be removed from this steam to turn it into our desired temperature of water. Every phase change will work similarly. You have to factor in thermal energy needed to change temperature, and separately the thermal energy needed to actually change the phase. So, we're going to continue on and continue this example to get in just a little more practice. The second part of this question asks, how many grams of ice would be needed to absorb the above calculated thermal energy if the ice starts at -6 Celsius and ends as positive 45 degrees Celsius water? So the objective here is, we had our steam, it needs a certain amount of energy removed from it to turn it into 45 degrees Celsius water. We're going to accomplish that by adding a certain amount of ice into the same chamber. So imagine you had a sealed vessel of steam and you throw some ice in there with the steam, you lock the box, and eventually the ice will absorb heat from the steam, and both the ice and the steam will eventually end as a combined pool of 45 degrees Celsius water. The goal is for them to end up to mix together as water at the same final temperature. So we need to figure out how much ice is needed in order to accomplish that goal. And the math will be similar, except that we're now going to be solving for a different variable in the formula. Like before, we're going to need to set up every single step in this process. So, change in heat for this ice. We need to heat the ice up. It's going to eventually melt into water and warm up to 45 Celsius. That first step is going to be warming the ice up to its melting point, because it's not going to melt at -6. You got to warm it up to 0 first. So, we need the mass of the ice, specific heat of ice, and the change in temperature of the ice. Note that change in temperature is always final minus initial, so that's going to be 0 minus -6. We're going from -6 up to 0. That's an increase of 6 degrees, and inputting it like this will give us that +6 that we need. So this will be a positive number. Once we've got the ice up to its melting point, then we need to actually melt it using ml, specifically for the latent heat of fusion for ice. We will look up that constant in a second. So this is required to actually perform the phase change. And then the last step, once we have melted it into 0 degrees Celsius water, now we need to warm that water up to 45 Celsius. So now we'll need the mass of the ice times the specific heat of water. Again, we've done the phase change, so now it's water, and we need to use water's properties, times that change in temperature. End at 45, start at 0, so that'll be an increase of 45 degrees. Now, the one variable that we've been asked to find here is the mass of the ice. That's the one thing that we don't know. That's the thing that we're going to solve for. So, previously we were solving for total Q. Now we actually know total Q because earlier we found the energy that needs to be removed from the steam, and that's the energy that the ice is going to be absorbing. So our delta Q will actually be positive 252,038 because the ice is what needs to be absorbing that thermal energy. So We know Q this time. It's going to be positive, the positive version of the number we already found, equal to, we don't know mass of ice. Our MI is going to be the same throughout this whole part, but we still don't know it yet. But keep in mind it's the same mass for every single piece of this equation. Mass of ice times specific heat of ice. I looked on the table a second ago, and that specific heat was 2090. So that's what will go there. Our change in temperature is going to be positive 6. The next term is the latent heat term, so mass times the latent heat of fusion for ice. We'll quickly look back at the chart for that again to pull that number from. So water latent heat of fusion is 3.33 times 10 to the 5th. So that is the value that we'll plug in for the latent heat of fusion for ice. Then the last term is warming up the newly melted water, mass of the ice times specific heat of water. Again, it's changed phase, so we need to use the water specific heat instead, times the temperature increase. Now, it's the same MI across all these terms. It's the same variable in 3 different places. So we're going to be able to utilize the distributive property to help us out in a second. First thing I did is simplify each term so that there's just a constant times MI. And since this is a bunch of things being added together that all have a single MI term in it and no other unknowns, we can add them up as normal. Do note, as opposed to the previous example, everything here has become a positive number since we have to add thermal energy to the ice. The MC delta T's will already be positive, and we just have to manually decide the ML term is going to be positive because you have to add thermal energy to ice in order to turn it into water. So we'll take our separate MI terms. We can linearly add them together, and then all we have to do is one more piece of division to get our final answer of 0.45 kilograms of ice. So that's the mass of ice and needs to be added into the box with the steam so that the whole thing, both parts, end united as 45 degrees Celsius steam. So that's kind of 2 phase change examples worked into one there. For any phase change, you need to separately track the energy needed to change the temperatures and the energy needed to actually induce the phase change. So keep those in mind as you're working examples like this. Now, next, sort of the last central concept of the Chapter 11 material is the rate of thermal conductivity. Conduction is something we've talked about. Conduction is specifically when heat transfers between 2 objects that are in direct thermal contact with each other. They're touching, and thermal energy can flow from hot to cold through their connection. We talked briefly about the other 2 types, convection and radiation, and we're bringing this back up now because we're now going to start putting some math into conduction. We're going to figure out how to calculate the rate of conduction. If you'll recall, I mentioned previously that the human skin does not have a thermometer built in. You can't touch something and know what temperature it is. What you sense is how quickly thermal energy is exiting you or entering you. If something feels really, really hot, then that's a lot of thermal energy entering your hand very quickly. That's a high rate of thermal conductivity, a lot of joules per second. And we're going to, in a moment, begin calculating or figuring out how to calculate that magnitude of thermal energy flow, the amount of joules that flow into or out of something every second. There's a few more images on this slide, kind of as a brief review of the thermal energy transfer concepts. The pot of boiling water is meant to sort of represent convection, since there's convection currents inside of the hot water, and additionally there's convection currents of hot air and hot steam as a result of the heat from the pot and the evaporating water. But I want to briefly sort of compare radiation and conduction together, and we're going to do that with this. We're going to do that with this thermal image of a house. So, this is a thermal image, and thermal cameras and night vision and stuff like that. What they do is they detect infrared radiation coming off of an object. And infrared radiation is just one of the many forms of radiation. Light is a type of radiation, gamma rays are radiation. They're all part of the electromagnetic spectrum. And objects that possess energy often will radiate energy out in one of those forms. Most commonly, objects with thermal energy tend to radiate some of it outwards as as infrared energy. And so humans have developed technology that lets us basically detect infrared radiation and create an image out of it to let us, see in the dark or be able to see warm objects or warm creatures where we normally wouldn't be able to detect them. This particular image here is a thermal image of a house, and the brighter parts of the image, like the windows, represent areas that are giving off lots of infrared radiation and are giving off lots of thermal energy, whereas the darker parts, namely the roof, it's so dark you can't even see it, are giving off less or possibly no infrared and possibly no thermal energy. So, in some ways, this does tie radiation into conduction, because if something has a lot of thermal energy, you could get thermal energy by touching it, but that object will also just naturally give off some of that energy in the form of radiation. So that's one thing to keep in mind. But the main thing I want to focus on in relation to this image and this house is conduction. Now, this thermal image's purpose is to show us which parts of the house have more thermal energy coming out of them than others. The brighter parts of the house are radiating more, they're giving off more energy than the darker parts of the house. And I want us to briefly consider which specific pieces of the house are giving off more thermal energy. Namely, the biggest offender here is the windows. Now, in the construction world, you build a house and you insulate the house because you want the inside to stay a comfortable temperature no matter what's going on outside the house. As an example, this is a cold winter day, there's snow in this picture. It's kind of hard to tell because it's a thermal camera, but there is snow on the ground and snow on the roof. So on a cold winter day, you want the inside of your house to be warm regardless of how cold it is outside. But by virtue of the fact that thermal energy always transfers from hot to cold, and as long as the air inside your house is touching the walls of the house, which are also touching the air outside of the house, a certain amount of thermal energy is always going to be traveling out through the walls into the cold outside. Over time, your house is going to cool down no matter how well insulated it is, just by virtue of the fact that, the warm things inside are touching the walls, which then touch the cold outside. So thermal energy will always flow from hot to cold. And in the construction business, you then have to install air conditioners and heaters to make up the difference so that the inside stays at the same temperature. But what we care about mostly today is looking at what parts of the house are giving off more thermal energy. Because as we start looking at the rate of thermal conduction, the speed at which energy transfers, various different factors can affect that. Various different factors can affect the speed at which thermal energy travels through a certain object. As it relates to this picture, let's focus primarily on the windows. The windows are where most of the thermal energy is exiting this house, and frankly that's true of pretty much every building. The windows are always kind of a weak spot when it comes to keeping a building's temperature constant. And the reason for this is windows are very thin, and windows are made out of glass. They kind of have to be so that we can see out of them. It's the entire purpose of a window. But they are thin, they are glass, and by virtue of their size and what they are made out of, thermal energy is able to pass through that thin pane of glass faster than it can pass through the walls of the building, which are made out of things like wood and insulation material on the inside. What the part of the building is made of affects the rate at which thermal energy can travel out of it. Additionally, the temperature gap on one side to the other also affects this. For example, if it's really hot inside and really cold inside, that's a big temperature difference, and that makes it easier for thermal energy to try to get from hot to cold. Whereas if it was the same temperature inside and out, then there wouldn't be any net energy flow because the energy levels are the same on both sides, and there's no real need to go from point A to point B. There's no influx. There's no balance to try to restore. So, from this house, we can see that different objects, depending on various properties, allow energy to pass through them at different rates. And in a minute, we're going to start quantifying how to measure that. Now, first, before that, I want to ask you to cast your mind back to when you woke up this morning. I want to try to illustrate a certain point to you. Now, when you go to bed at night and you're asleep for hopefully around 8 hours, all of the objects in your room sitting still in the dark should equalize to about the same temperature overnight. Nothing's moving, there's no lights on, so there's no new energy being introduced to the room, and everything in the room is allowed to equalize because it's all touching the same air, some of the objects are touching each other. Everything in your room should be about the same temperature as you wake up. So let's just say, for example, everything in your room should be about 70 degrees. You then wake up in the morning and you start interacting with various objects around your room as you wake up. You touch, say, your blankets, you touch your clothes, and those objects feel pretty neutral. You don't really notice any sort of a temperature gap when you touch them. They're about 70 degrees, but they don't feel cold. But then, maybe perhaps you touch something metal, like you pick up a metal object, pick up some jewelry, pick up a metal phone case, pick up a metal cup, or perhaps even your feet touch the floor, which might be made out of linoleum or stone or something like that. And all of a sudden, those objects feel cold. But they're all still at the same temperature as everything else because they've equalized overnight by touching the same temperature air. Everything in your room is 70 degrees, but certain things still feel colder. For example, I, within my own office right now, have several pieces of paper, as teachers tend to do, and I also have this microphone that I'm currently using. Now, this microphone is made mostly out of metal, and when I touch it, it feels measurably colder than touching this pad of paper right here. They're at the same temperature, but the metal feels colder. The reason metal feels colder is the material it's made out of has an inherently higher rate of thermal conduction based on what it's made of. And because of that, it's able to suck thermal energy out from my hand faster. Certain materials, like, say, styrofoam and wood and paper, have very low rates of thermal conductivity. They don't absorb thermal energy very quickly, and they don't give thermal energy off very quickly. So even if they're a high temperature, they might not feel like they're a high temperature because, again, your skin cells don't have a thermometer built in. They just detect the rate of energy flow. You could touch something that was 200 degrees Celsius, and if it was an insulator, you might not actually realize what its numerical temperature is if it's not actually giving off energy into your body very quickly. Whereas metals and stone and things like that have a higher rate of thermal conduction, and so even if the temperature difference between it and you is very minor, the change still feels more pronounced because the rate is still going to be higher because of the metal. So, heat always flows from hot to cold. The rate at which heat flows depends on the object it is flowing through. And now we're going to start quantifying that. So, there's a lot of information on screen. We're going to go through it slowly. All right, so there's a lot of information presently here. The main thing I want you to focus on for right now is this formula here on the... I take that back slightly. We're going to focus on one other thing first, one other small thing first, and it's this little piece right here, P equals Q over delta T, which should, hopefully, look familiar. P equals Q over delta T. This is the old formula for power. Power being the rate at which work is done, but alternatively being the rate at which energy is used or transferred. This is the same power, actually, from physics 1500 that measured, like I said, the rate at which energy was used or transferred between two objects. And the transfer of thermal energy, the rate of transfer of thermal energy, technically meets that definition. It's the flow of energy, Q, over an amount of time, T. So power is actually the unit we're going to be using for thermal conduction, the rate of thermal conduction. So capital P here is power, and it's still measured in watts like it was before. 1 watt equals 1 joule per second. So 1 watt of thermal power means that 1 joule of heat is transferring through an object every 1 second. I use the term thermal power just there. Rate of thermal conductivity and rate of thermal power are synonyms because, again, power is defined as the rate of energy transfer. So since they're synonyms, I might use them interchangeably. Certain assignments you have in this class could also use them interchangeably. So first takeaway is that P, thermal power, is the rate of thermal conduction, and that's the variable it's going to appear as in the formulas. Next, the formula on the bottom here represents how all of the various factors that can affect the rate of thermal energy transfer work together in order to create the actual final power value. And we're going to look at each part of this formula one piece at a time. So power is equal to, first thing we're going to talk about is the TH minus TC term. This refers to the change in temperature from one side of an object to another. For example, let's say I'm going to use this sort of pad of sticky notes as a representation of a wall. So like the wall of your house. Now this wall, if you've built a house and it's a cold winter day out, then you very intentionally want the inside of the house to stay warm and the cold on the outside of the house to stay outside of the house. And if one side is hot, the other side is cold, that's going to form a temperature gradient. So say you've got it set to 80 inside and it's 30 outside. That's a difference of 50 degrees. And that difference, because there's a difference in temperature, that's going to cause thermal energy to try to move from the hot side to the cold side however it can. And in this case, it's going to transfer through the wall itself. So this formula is designed to be used to find the rate of thermal conduction through an object as thermal energy goes from one side of it to the other. If we were looking at the thermal energy passing through the wall of a house, it'd be the energy going from the hot side to the cold side. And the rate at which that energy flows does depend on the temperature difference. The bigger the difference, the faster the energy is going to flow. We've got a lot of thermal energy over here and not a lot of thermal energy over here. Excuse me. Thermal energy is going to try to move like water via osmosis from high concentration to low concentration. So the more thermal energy, the bigger the temperature difference, the faster the thermal energy will flow. Again, referring back to if you touch something that's really, really hot, more thermal energy will enter you more quickly because there's a bigger difference between it and you. So that is one factor that affects the thermal power calculation. Next factor I want to look at is the A term here. That is going to be the surface area of the object in question. I'm going to keep using this to sort of demonstrate a wall. If this was a wall, it has a certain flat surface area on the outside and on the inside, and that surface area is the amount of space, the amount of surface it has that is touching the air on either side. And the bigger the wall is, the bigger its surface area, the more air it can be touching on either side. Therefore, the bigger its area, the faster thermal energy can pass through it because there's more space for the energy to transfer in. It's kind of like building a bigger door on your auditorium. If you've got a really small door, only so much can fit through it at once. But if you've got a really big door, that's more space for things to get through. So, area, the size of the object, the flat surface area that the heat will transfer through, also affects the thermal power. So that's the next thing. The next term we're going to look at is the L term down here. This is the length that the thermal energy has to travel through. But if I was to use a different word to compare it in the case of our wall right here, it would actually be how thick the wall is. Recall again the picture from a few slides ago, which I can just show again, of the thermal energy flow out of this house. The windows have the most thermal energy coming out of them, and there's a few reasons for that, but one of them is just how thin the windows are. They are far thinner than the thickest part of the walls of the building. And if the object is very thin, if the thermal energy does not have very far to travel, that's going to speed up the process, which is why this L term is on the bottom here. If L is smaller, that's going to drive your power up. But if L is bigger, if the object is really thick, that's more distance the heat has to travel before it can finish going from one side to the other. So if L is bigger, that's going to make P smaller because L is in the denominator. So it's not just the width and height that count, so too does the depth, how thick the object is. The thicker parts of your house wall insulate better than the thin panes of glass in your window. The last term in this formula is the K term, and this is the term that represents what the object in question is made out of. Because, as I've hinted at already, different materials allow thermal energy to pass through them at different rates just based on what they're made of. So this K term, it's a new constant. It's the thermal conductivity constant. And as with all the new constants so far in this class, it's going to come with a new chart to keep track of them. Again, you don't have to memorize any of these. The table will be available to you when you need it. And this table shows the various different thermal conductivity constants of a bunch of different materials. Now, these numbers, the size of the number, represents how much energy can pass through the material every second. So a bigger number, like up here with the solid metals, a bigger number represents that more energy can travel through every single second. So these materials up here, these metals, have very high thermal conductivity. Energy can transfer them very quickly. Whereas these gases and nonmetals down here have much, much lower values. Thermal energy does not transfer through them nearly as fast. I think a big standout here is actually air. It's tied for the lowest value on this table, 0.0234. Nonmetals and gases are good insulators. They don't allow thermal energy to travel through them very quickly, usually because of how, at least in the case of gases, the fact that they're not very dense. So what it's made of matters a lot. And one small thing to keep in mind, just looking at the numbers on this table, is that air is a very good insulator. Air does not let thermal energy transfer in and out of it very fast, and that's one reason why you tend not to notice or care much about the air's temperature if you go outside, unless the temperature is just awful. Like if the temperature difference is more than maybe 10 degrees, then you're going to start noticing it. But even in the heat of sun, as long as you're in the shade, you'll feel a lot more comfortable because most of the heat, if it's a summer day, comes from the sunlight, not from the air itself. You'll get more energy from standing in the sunlight than you would standing in the shade just touching the hotter air because, again, the air doesn't let the thermal energy flow very fast. And this is one reason why most actual windows these days, rather than being a single pane of glass, they tend to be two panes of glass with an air layer in the middle. Since the air is a really good insulator, better than glass is. Glass is still pretty alright as an insulator, but air is even better. And so we kind of use air as an insulator sometimes. It's quite literally the best insulator on this table. So, the factors that can affect the rate of thermal conductivity, the rate of thermal power are the K constant representing what the object is made of, its surface area exposed to the temperature difference, the temperature difference across its two sides, and how thick it is. And now we're going to use this formula a couple of times. So, this particular example is about a pot on a stove, and that's going to be a pretty common example that is a pretty common situation that comes up in questions regarding this concept. The next most common one will be about walls, like actual construction building walls, and we'll look at another one of those in a minute. For right now, we're just going to focus on this question about a copper-bottomed pot. So whoever is... excuse me. This person has a pot. The bottom is made out of copper. They have filled it with ice-cold water. So ice-cold, meaning that it is at 0 degrees Celsius. And they're setting it on top of a stove eye to start warming up the water. The eye of the stove is 300 degrees Celsius, so that is informing the temperature difference from the underside of the pot to the inside of the pot. The pot has a diameter. It's a round-bottomed pot. I've only ever seen round ones personally. That has a 12 centimeter diameter, and the metal that makes up the pot is 2 millimeters thick. With all of this information, are we able to determine the rate of thermal energy flow, the power flow, through the bottom of this copper pot? So, to set the stage, ice-cold water is in a pot put on the stove eye. The eye of the stove is very hot, the inside of the pot is very cold, so that is a temperature difference. That is a temperature gradient. And thermal energy is going to flow from the hot through the bottom of the pot into the cold water. And we have to figure out the rate at which it's going to do that. So, let's quickly glance at our formula here. We're solving for power, so that's going to be our unknown. For K, we know what the pot is made of. It's made out of copper. So we can tab back to the previous slide and find the thermal conductivity constant for solid metal copper, 397. So that's the value that we will use for that K. A, the area term is a little bit tricky here. Again, the bottom of the pot is a circle. It's round. And we do know the diameter of that circle, but the question doesn't specifically give us the area of the circle, unfortunately. But if we dig up a little bit of geometry knowledge, we can use the diameter to find the area of the circle. The area of a circle is defined as pi times the circle's radius squared. So pi r squared, not pi r round. And as a quick reminder, diameter represents the entire width of the circle, whereas radius only represents from the center out. And radius is what we need for the actual area formula, and we need to find that area before we can solve the rest of the question. So for this little aside formula here, I've plugged the radius of the pot into the formula. So if the diameter is 12, the radius would be 6 centimeters. I then converted 6 centimeters into 0.06 meters, because that's going to give us an area of meters squared. If you were to plug in 6 centimeters instead, your area would be centimeters squared, and then you'd have to deal with a different conversion later on. So I converted up front to avoid that. This would give us an area for the round bottom of the pot as 0.0113 meters squared, and that's the A that we're going to use in the formula. The next term is the temperature gradient, TH minus TC. The hot side is the I at 300. The cold side is the ice cold water inside, which must be at 0 degrees Celsius for it to be ice cold. So our temperature gradient will just be 300 minus 0, a difference of 300 degrees Celsius. Since this is basically a delta T, it's not actually, like, it doesn't say delta T in the formula, but it is still one temperature minus another. This has the effect of a delta T, where it can be Celsius or Kelvin, and there won't be an issue. No problems in using Celsius here, as long as you use 2 Celsius temperatures or 2 Kelvin temperatures. Last term is the pot's thickness, the L term right here. That is 2 millimeters thick. I went ahead and converted that into meters, since that's the unit we want to use as a standard. 2 millimeters is 0.002 meters. That gives us everything we need to solve for our final power of 673,494.6 watts. That's a lot of energy. 600,000 watts would be 600,000 joules transferring every single second. That's very fast. And this pot is designed to make that rate of thermal energy flow very fast because they made it out of metal, they gave it a reasonably sized surface area, and they made the metal very thin. If it's metal and if it's very thin, thermal energy will transfer through it very, very fast. And that's the point of cookware, is to take heat from the heat source and transfer through the metal to get it into your food. So this object is working as intended. Now, there is one problem with this formula that we've been looking at here. I'm going to tab back for a minute. This formula is wonderful. It works. It's nice and convenient. The one of the main problems with it is this formula only works for objects made out of a single material. The pot in the example we just worked is made out of copper. That's just one material. It's 2 millimeters thick of just copper. But this formula doesn't work if you were, say, trying to figure out the thermal energy flow through the wall of your house. If your wall was made out of a layer of brick or a layer of wood, a layer of insulation, a layer of drywall. Most building walls are composites. They're made of a bunch of different materials stacked one after the other to make something better than each one would be by itself. And this formula doesn't quite work for that because you can only plug in 1K for one single material at a time. So the American construction and architecture industries realized that this formula needed to change a little bit because it's pretty important to architecture that you know that the walls of the building you're building are insulated, because you want people to be able to stay cool in the summer and hot in the winter, and not vice versa. You want to make sure the building keeps the heat where they want it and keeps it away from where they don't want it. So the formula had to be changed somewhat to be able to accommodate those hybrid composite materials. And so some very smart people created this variation of the formula. Instead of P equals Ka times the temperature gradient divided by L, they basically combined the L and K terms together. And they created a new constant. I feel bad giving you another constant right after the last one. But instead of the K constants that represent the exact thermal energy flow through a single material that you can calculate for any thickness, the American construction industry decided to create instead this R constant here. And the R constant represents the rate energy can flow through specific materials of predetermined thickness. For example, if we look at this chart of R values, we can see that hardwood siding that is 1 inch thick has an R value of 0.91. Bricks that are 4 inches thick have an R value of 4. There's multiple entries here for fiberglass depending on how thick it is. This formula has changed itself in such a way that now what you would do instead of plugging in a specific K and a specific L for the dimensions of your object, now what you plug in is the sum of all the R's that form the layers of your object. Note here, this isn't just R, this is sigma R. And if it's been a minute, the sigma on the front of something means that you want the sum, the total of all of that thing present. So this represents if you were, say, wanting to figure out the rate of thermal energy flow through a wall that had a layer of brick, followed by a layer of wood, followed by a layer of insulation, then you would take the R values for each of those things and add them all together. The sigma R is the sum of all the R's for all of your individual layers. And this is the version that is used in the American construction industry because they tend to work with like pretty regular, like regulated materials. Like most drywall is the same thickness. Most exterior walls and most bricks are the same thickness. And so they didn't really need the flexibility of being able to plug in L. What they needed was a way to find the thermal energy properties of their composite walls. So they sacrificed one piece of versatility to gain a different piece of versatility. And so this is the formula that you would use to find the thermal energy rating, the thermal power through any sort of composite material, like a wall made out of multiple layers of multiple things. And it's very convenient. I find it convenient, at least. Adding the R's together makes sense as a system. What frustrates me about this version of the formula is, since it was developed by the American construction industry, it uses American imperial units as opposed to the metric system. Instead of meters, it's got feet squared. Instead of Celsius or Kelvin, it uses Fahrenheit. Instead of joules per second, it uses British thermal units per hour. A British thermal unit is another energy unit that's, in my experience, not super commonly used, but apparently someone in the construction sector uses it. And that means that if you use this formula and this table of constants specifically, then the P you get out isn't going to be watts or joules per second. It's going to be BTU per hour. And you're going to have to plug in feet squared for A and Fahrenheit for your temperature difference. In my opinion, it's the biggest pain about this particular formula, but it is worth noting for when this does come up in questions. I'd like to demonstrate how to use this one real quick. So let's look at a construction question where we build a wall out of more than one type of material. It's the hottest day of summer. It's 110 degrees Fahrenheit outside. The walls of your home are made of 4 inches of brick, followed by 1 inch of fiberglass, and then a standard industry sheet of drywall. Said walls are 10 feet tall by 20 feet wide, and the inside of the building is set to be 70 degrees Fahrenheit. Our question: what is the rate of thermal energy flow through this particular wall? So, since we're dealing with a composite wall made of multiple materials, I've got the materials themselves listed here, and a shortened version of the chart that has just those R values on it. We're going to start plugging things into our modified imperial version of the formula. So, for our A term, the wall was 10 feet by 20 feet, so that's going to make our area about 200 feet squared. Our temperature difference, and this is the one time where we actually want Fahrenheit, is 110 minus 70, so a difference of 40 degrees from inside to outside. And then lastly is the sum of all of the R's. So we have one 4-inch layer of brick, that R value is 4. 1 inch of fiberglass, that value is 4.35. And lastly, standard industry drywall is 0.45. And so all of those will get added together and plugged in for sigma R. And this would tell us that the power through this particular wall would be 909 British thermal units per hour. I didn't write the hours part. I apologize. Now, BTUs are weird. I don't hardly ever use them, but they measure the same thing as power, so you can convert them into and out of you can convert them into and out of units like energy and watts, joules and watts, excuse me. And if, hypothetically, we converted this and found our answer to be, 266 watts, that means that every second, 266 joules transfers through this wall. Now, if you want the inside of your building to stay the same temperature all the time, then you are going to deal with heat flowing through the walls. It's going to happen. It's inevitable. You can't stop it. So if you want the house to remain the same temperature all the time, what you need is an air conditioner or a heating unit, depending on the season, that's able to deal with that rate of energy flow. Say it's a cold winter day and you're losing the energy flow out of your walls is 266 watts. That means every single second your house is losing 266 joules of thermal energy, meaning that to keep the inside of your house from getting colder, the heater would have to make 266 joules of thermal energy every single second in order to keep up with it. And this is the way in which this math is utilized by people in the construction industry. And with that is all of the concepts related to Chapter 11 for Physics 1500. As always, please let me know if you have any questions as you're working on assignments or going over this material. And Chapter 12 will be about the laws of thermodynamics, what they are, and how we utilize them in physics and in other categories as well. Thank you very much. See you then, and have a wonderful day.